that will be given at the end of our session. So you may give a response to the webinar, any comments for improvements to this webinar series. All right. So, and if you have any questions, also you can pop up the questions at the chat box as well. Okay. But before I start, I would like to share with you guys a little bit information about our speaker today. Professor Dr. Mohammed Sharawi is currently a professor of electrical engineering at Polytechnique Montréal at Montreal, Quebec, Canada. He is also a member of the Polygrams Research Center at the Polytechnique. He was with King Fahd University of Petroleum and Minerals, known as KFUPM in Saudi Arabia between 2009 until 2018. He founded and directed the Antennas and Microwave Structure Design Laboratory, AMSDL, at the KFUPM. Previously, he was a visiting professor at Intelligence Radio, Radio Laboratory, in Electrical Engineering departments at University of Calgary, Alberta, Canada, during the summer-fall of 2014. Previously, in the previous year, he was a visiting research professor at Auckland University during the summer of 2013. Professor Sharawi's area of research include multiband printed MIMO antenna systems, reconfigurable and active integrated antennas, applied electromagnetics, millimeter wave MIMO antennas, and integrated 4G and 5G antennas for wireless handset and access point. He has more than 300 papers published in referred journals and international conference, 10 book chapters, one single authored book entitled Printed MIMO Antenna Engineering, published by Artec House in 2014, and the lead author of the recent book entitled Design and Applications of Active Integrated Antenna, also published by Artec House in 2018. He has 20 issued and 15 pending patents in the US Patent Office. He is serving as the associate editor for the IEEE Antennas and Wireless Propagation Letter, AWPL, RET Microwave, Antennas and Propagations, MAP, and an area editor for Wireless Microwave and Optical Technology Letters, MOP. He is the specialty editor of the newly launched Frontier Journals of Communications and Networking, the System and Testbed Design sections. He served on the technical and organizational programs committees of several international conferences, such as EUCAP, APS, RMWS 5G, AppCap, iWallet, among many others. So without further ado, Prof, I would like to welcome you to present your webinar. Please welcome.
Thank you very much, Dr. Sedatul, and for this very nice long introduction. And I would like to also thank Professor Azrami and Professor Pringjak for the invitation and taking part of the series of webinars that you guys are conducting. So it's a pleasure to be here. It's interesting. There's exactly 12 hours difference between us. So it's 10 a.m. there, but it's 10 p.m. over here. Finally, I would like to thank the audience for deciding to come and listen to me talking rather than going to the beach and having some fun. All right, so let me turn on my slides. I hope that you can see now. Are the slides clear? Can you guys see one slide, the regular page?
So far, yes, so good for us, Prof. So far, so good.
Yeah. Excellent. Okay, thank you. So today, our talk will be entitled Active Integrated Antennas, Fundamentals and Applications. And it's basically a collection of works that we've been doing, especially focusing on a new paradigm of designing the antennas with the active components, and that I will focus on towards the end. But at the beginning, I will also give some background about this area. The presentation scope will go as follows. First, I'm going to give some kind of a highlight about our research activities here at Polytechnique Montreal, and especially my group in specific. Then we're going to go over some technology trends and why are we driven by this kind of force and tendency to keep on evolving our antenna systems to keep up with the market needs. Then I will move on to the definitions and the types of different active integrated antennas and the methodologies that were used in the past. Then I will go on and describe in details with several examples the co-design approach that we have developed several years back with some very interesting outcomes. And then I will give some highlights and future challenges about the future of antennas in general. So just to give you a perspective about Polytechnique Montreal, it's an old university. It was actually founded in 1873. It's the oldest in Quebec and the biggest engineering school here. It is part of the University of Montreal schooling system. We are only focusing on engineering. So at Polytechnique Montreal, it's just the engineering deanship of the University of Montreal. We have 7 engineering departments with about 8,000 students only in these engineering departments. So all the other students, the population in the University of Montreal in the humanities and stuff are not counted. So the total will be exceeding 20,000. We have more than 700 students in electrical engineering alone, with about 150 graduates in the department. For just a closer look about the location, in Montreal, there is actually a small mountain. Well, it's a big mountain, but in width, but it's small in height. But that's why it's called Montreal, and then this name came as Montreal for the city. This is the location of Polytechnique, and this is a night view in the winter time. You can see the snow on the side and at the top. And it was a pity that this year the APSRC was supposed to take place here in Montreal. I was part of the organizing committee. We've done a lot of work, but then everything went to an end with a small, tiny particle that invaded the world and made our life very, very, very difficult. Okay, so just to give you a quick perspective about my research group activities, basically it spans different kind of sectors. We focus on handset-based antenna systems, base station antennas, covering, of course, MIMO, massive MIMO. We started with 4G, and we are continuing to 5G, and then hopefully towards 6G and above 100 gigahertz based systems. We are also doing a lot of projects, and we have concluded several projects for RF sensors and arrays in biomedical and oil and gas industry, especially when I was at QPM. We're still continuing the research on energy scavenging and the ideas of rectifying antennas and the like. Of course, whenever we talk about antennas, we're talking about different methodologies, different techniques to make them smaller, more efficient, with some kind of interesting properties. We have to also consider antenna arrays, and we've done that for UAVs, for UGVs at microwave bands. We've done several designs at millimeter waves, and now we are trying to push it a little bit beyond millimeter waves. And of course, the classical computational electromagnetics and some of the numerical techniques that we have touched upon, like the theory of characteristic modes, the characteristic-based functions, and the antenna current green functions. Here are some of the examples that we have done in the past, from reconfigurable-based MIMO antennas to millimeter wave-based DRAs, and then to RF sensors for oil and gas industries. And you can see, our work spans a very large spectrum, going from several hundreds of megahertz up to now we're talking about millimeter waves going up to 60 and 100 gigahertz. At Polytechnique Montreal, it's the research environment is a little bit different than all the other universities that I have been with, because in the classical way in classical universities is that each professor will just close on himself. He has his own lab, he gets his own money, he builds his own capabilities, and that's it, and nobody touches his stuff. But here at Polytechnique Montreal, it's different. We have one big research lab, it's called the Polygrams Lab, where actually about 8 professors share all the equipment and also pump in the money to acquire new equipment and share it with others. So now we can measure the S parameters up to 1 terahertz. We can measure radiation patterns up to 500 gigahertz. We have all kinds of CAD tools, all kinds of fabrication facilities. We have a clean room. We have all milling and etching processes. And this year, I acquired the first reverberation chamber for MIMO testing that can do sub-6 gigahertz as well as millimeter waves up to 40 gigahertz, which is the one you see here on the right, on the down right corner of the screen where my pointer is. So we just got this from IMITE, a company based in Spain, and we can do 8x8 MIMO channel capacity measurements. So we can actually measure the correlation coefficients, and we can measure the channel capacity, not just calculate them based on the theoretical models. Okay, so that was the part about some of our capabilities and what we can do. Now, what is the driving force behind all of this? The driving force is our need and hunger for more connectivity, for more applications, for having the the ease of life of controlling everything from our mobile device, for example. We want to automate our houses. We want to check our health indicators. We want to know where our kids are. Everything to be placed in one small, tiny device. Of course, it's connected to other networks, but this is the ultimate goal. Of course, up to 4G. If some of you are as old as I am, you have witnessed the whole evolution of these kinds of different wireless systems. And up to 4G, we were still talking about mobile handsets or mobile technology. But when we jump from 4 to 5, there's a big paradigm shift, in a sense that in 5G, it's not about higher data speeds or data rates. It's not about having your mobile phone do more. It's about a complete change in the way we see the world connected. And this is a picture that I got from the European Commission, and it's very descriptive in a sense that it's showing you what 5G is going to be. We are going to have everything talking to everything in a sense. So everything is connected. I raise my flag when it comes to privacy. Our privacy will be much, much less with this kind of technology because you'll be exposed in a lot of things. Even your underwear will have sensors that will tell, the network what is the status of your body. So we're talking about massive connectivity, and this needs a lot of technological advancements when it comes to the mobile phones, when it comes to the sensors, when it comes to the networks. So we're talking about now a big umbrella that will have a lot of things underneath. And this is what 5G is about. Of course, this is the well-known 5G triangle that actually encompasses 3 vertices covering almost all the applications that you can think of. When we talk about very high data rates and high throughput, yes, we are talking about enhanced mobile broadband, where we're talking about 5G speeds at millimeter waves going up to, a couple of gigabits per second, so that you can download a complete movie in few seconds. And of course, we will utilize millimeter wave bands, and we have a lot of challenges in there, but the industry have gone so far in that, and I will show you some examples later. The other vertex here shows another type of applications that 5G should cover, which are the applications that require extremely low latency, very fast response times. When you're in a car and you want to avoid an accident, you need extremely short response times, fractions of a second, to put the brakes on, to make the alerts, to engage into different kinds of actions in fractions of seconds. So you need very low latency when it comes to the communication within the network, because you're going to get your response from the network. So that kind of latency should be shortened down as compared to the latency that you can tolerate when you are downloading a movie. The third vertex here talks about massive machine type communications, where we are talking about very small data rates, but at a much larger scale. When we're talking about a field of let's say in a farm, a whole kettle where all your animals are connected to the network, and you know the status of each one of them. You have thousands of them. So you're talking about small sensors connected with long duration with the network, sending just pulses, just beacons of data, so that you can still manage and know the status of your small sensors, your small network, your large network with small sensors and low power. So this is where we talk about the Internet of Things. So a lot of small things with sensors with low power that can last for several years without changing the battery, but they are sending small beacons every second or every tens of seconds, because it's not important to check every fraction of a second. These are, some kind of telemetry, some kind of health signals that you can take them less frequently as compared to a vehicular or an ultra reliable and low latency based vertex, which is on this corner. And in between, you can find a multitude of applications, as you can see over here. So this is what 5G is going to be about. Now, going back to the main topic of this talk, we're talking about antennas and integration of antennas and active antennas. Now, I found this a very nice picture, a pictorial view of how the antennas actually have been developing throughout the past 2 decades or 3 decades, actually since the 80s up to 2020. So we're talking about 4 decades here, 40 years of evolution. As you can see here, we went from the regular monopole-based wire antennas that were actually at least 10 centimeters long going out of your phone, to printed-based antennas within the phone, going down into the technology, and then ending up with non-resonant structures that are used for IoT or the like. But these are non-resonant, very tiny based antenna systems. I wouldn't bet on their efficiency, but they are still useful in some of the applications. But this tells you how small we have become over the years. Another kind of technology-based chart that I want to share with you is this kind of roadmap. This is a very nice block diagram that is kind of anticipating the way the front ends for us antenna designers or researchers, how are things are gonna be or are supposed to be. So we're talking about a roadmap between 2018 and 2024. So we are now in the middle of this roadmap almost, where we are talking about at least 4 antenna elements in a MIMO configuration for the downlink, 2 antenna elements for the uplink, and then we have an array of millimeter wave MIMO. Of course, we can have multiple arrays, as I will show you in a minute, but this is the general or generic architecture that we will be dealing with from now on. And as you can see here, we did not even talk about the GPS module, the Wi-Fi, and a lot of other things. You see, there are a lot of connections here, a lot of layers that are considering a lot of different technologies that you need to have connectivity for. So this is only the front-end architecture, and you can see how complex it is going to become. And each one of these layers are going to have its own PAs, LNAs, power amplifiers, low noise amplifiers, switches, and filters. So this is a picture that we need to have in the back of our heads. So the antenna trends, we are always going for smaller size, more integrated, more multifunction based designs. Now, the drive for integrated antennas comes from the fact that there's always a trade-off when we do our antenna designs. So the trade-off is between efficiency, size, bandwidth, and gain. And of course, we have to always think of the integration of the antenna with the back-end electronics and the radio frequency front end. So the front end is actually the RF electronics that are connected to the antenna. So up until today, the majority of the work is being done such as you design your antenna with a certain impedance bandwidth, and this impedance bandwidth you are guaranteeing that you will have a good kind of matching to 50 ohms, and then you will design your electronics based on the 50 ohm match. Of course, any kind of mismatch, you will start losing power or losing efficiency. Now, this drives our need to have more integration on the antenna side. We have a lot of standards, we have a lot of applications, so we need multi-band, multi-function based antennas. And this antenna goes at least 10 years back, where we had different antennas at 3G with diversity and so on and so forth. And you can see how primitive this antenna, this design was. Now, if we compare it to the mobile phones in our pockets nowadays. Another design from several years back as well shows the multi-layer, the multi-antenna systems that are being used as well, but still it's not as complicated as what we have in our pockets today as well. So this is the early 4G based antenna or mobile phone with two diversity antennas or supporting 2x2 MIMO only. So basically, when we look at where are we heading, integrating or going from 4G to 5G, 4G focused on having two antennas. Now, when we are designing our current phones, we are going to guarantee that we will have at least 4 antennas supporting 4G bands, in addition to several antennas on the sides of the phone that will support the 5G bands at sub-6 gigahertz. We are talking about 8x8 MIMO at least. And we're talking about 2 to 3 millimeter wave based arrays on the rim, on the sides, or on the package on the back of the phone. So you can see here the technology, the number of antennas per handset is becoming very dense. The technology is evolving very fast. The demand is very high, and we need to accommodate all of these things in a very efficient and smart way. On top of that, we're gonna have, of course, all of our phones, the majority of them, we have a full screen at the front, so you cannot do much. And thus, this complicates the design and pushing the antennas towards the side or the rim or the back near the casing. Or we're also investigating, some people are investigating putting things on the display, although the display will be actually facing your head, but there are some groups are doing that. So the key answer or the key word here is miniaturization. Miniaturization and integration, as we will see momentarily. Now, when we put all of these things in perspective to see where we stand today, some of you have heard that already Qualcomm has deployed their 5G modems with their 5G antenna arrays within these RF front ends. I will show you some detailed views later. But we're talking about supporting 4x4 MIMO at 4G and 2x2 MIMO at millimeter waves 5G. This is what has been standardized so far. We're talking about 800 megahertz at millimeter waves or more. Of course, Huawei or Sunrise in Switzerland already demonstrated sub-6 gigahertz massive MIMO for 5G, and South Korea has demonstrated 5G speeds as well with Samsung. As well as in the market nowadays, you can find some 5G ready smartphones from Huawei, Samsung, Pixel, and so on and so forth. So the question is, what can we add? It's not the end of the story. Of course, what we can add is more efficient and more highly integrated antenna systems. And the key word that comes in here is active antennas. Of course, active integrated antennas is a a title or an acronym that is highly tied to antennas that are intimately integrated with active devices, rather than just connecting the 50 ohm to 50 ohm. Of course, the conception, the first AIA appeared in 1928, but that was at extremely low frequencies. And of course, the concept kept on evolving because of several main features. If we do the active integration in a correct fashion, we can increase the effective length of the antennas, we can increase the bandwidth, we can decrease mutual coupling between array elements, as well as we can improve the gain. Not just improve the gain because we are putting amplifiers, improve the gain because we are making a better, more efficient connection between the amplifier and the antenna. Of course, in the past, active integrated antennas were, an active integrated antenna was an antenna that included an active part. And the majority of them, I can claim 95% of the designs were based on 50 ohm, meaning that the antenna is optimized alone, the amplifier is optimized alone, and they are just connected like Lego together. Okay? But this is not very efficient. We can make it more efficient. And a lot of topics were covered for active integrated antennas in the past. They covered amplifiers, mixers, RX modules, and oscillators. So we can see some examples. This is an example of an amplifier integrated antenna. Again, the amplifier was here, the antenna was here. It's just a 50 ohm based match. Another example was an active integrated oscillator. This was a true active integrated antenna because the antenna and the amplifier are actually co-designed. Part of the amplifier stability is coming from the antenna radiating structure, but this is an oscillator, so it's not that useful. Some recent works are shown here. This is, again, an active integrated antenna, but these guys went back and said, okay, we need a 50 ohm match at this point. If you can guys see that my pointer, 50 ohm match at this point. So again, the patch antenna was designed alone, the amplifier was designed alone, they were put in one package and considered an active integrated antenna. So going back to some fundamentals, there are several types of active integrated antennas. There's the oscillator type, the amplifier type, the mixer type, the transceiver type, and other types of active antennas. Of course, the oscillator type will only provide the carrier signal. That is, we can change the frequency of this carrier signal by just changing the DC power. We have amplifier types from receiver or power amplifier to transmitter power amplifier or receiver low noise amplifier based. We have mixer type based active integrated antennas where we have direct mixing. So the signal comes in, it gets directly mixed within the structure or coming out of the antenna right away, and the multiplier, the down converter, is right after the antenna, rather than having a stage of filtering and then amplification and then mixing. So let's take a look at each one of these in a little bit more details. For the oscillator type AIAs, as you can see here, there are different architectures. We have to satisfy the Barkhausen criterion to maintain oscillations. So the total gain should equal to 1, and then the total phase should equal to 0, or 360 degrees. Now we can place the antenna in the feedback structure of an amplifier, or we can have a resonator in the feedback that will cancel out or that will resonate with the antenna and make the impedance of the antenna 0 along with the resonator. So the resonator and the amplifier will provide the negative impedance. The positive impedance of the antenna will get actually canceled out with this negative impedance. Of course, these kinds of oscillator type AIAs, they have high DC to RF efficiencies and low phase noise. They are useful in some applications. And here is one example. The efficiency was about 25% DC to RF efficiency. And as you can see here, the authors, actually, I know TJ Ma very well. They actually used a transistor. They optimized the two transmission lines around it to have them actually act as inductances. And then they added the capacitor here to actually help resonate this amplifier as an oscillator. and at the same time, they designed the length of these two sections to act as a radiating loop antenna, or a it's a loop antenna basically. Okay, so the oscillation frequency that was achieved was 5.3 gigahertz with several interesting matrices. Again, this was a truly active integrated antenna, because the antenna is part of the radiating. The antenna is part of the matching circuit and part of the actual amplifier design. A couple of other designs by the same group, as you can see here. They did it at also similar frequencies at about 5 gigahertz, but they achieved different kind of metrics in terms of gain, size, and efficiencies. The second type of active integrated antennas is actually the transmitting PA or receiving LNA. Of course, they can provide good power added efficiency, noise figure, and nonlinearity. And of course, we need to optimize these. The majority of these works were based on 50 ohm matching, as I will show you in literature. But a true design would actually take the actual antenna and the output matching network as the load to the amplifier and design it accordingly, rather than just doing 50 ohm. Same thing at the receiver side. We take the whole structure as the load, and then we actually consider it in the design of the amplifier itself. So we can actually achieve multiband, active loading, and MIMO if we follow some of these techniques, as I will show you later. Of course, some of the examples from literature, they are a little bit old, as you might see, but again, they are not truly active integrated, because each was designed based on a 50 ohm requirement. So here is one design at 2 gigahertz. Here are some other designs. This is at 5 gigahertz. This is covering GPS and SDARs that I have done about 10 years ago. Again, it was also based on 50 ohm, but it was an active front end, because we designed the amplifiers as well as the antennas themselves. The third type is the mixer type active integrated antennas. And in this type, we actually integrate the antenna directly with the mixer. But as we all know, a mixer requires a reference signal or an oscillator. So part of this mixer circuitry, which is M1, this M1 is actually going to be designed as an oscillator. So this is called a self-oscillating mixer. So you have a self-oscillating mixer attached to an antenna, and by properly integrating the antenna with this self-oscillating mixer, we can have it resonate and operate at millimeter waves. This is working at 60 gigahertz. And as you can see here, we can have some very good effective conversion gain with a very small footprints. But again, the design over here was optimized, of course, for a certain application. But this is a true active integrated mixer that appeared in literature, co-designing the antenna with the mixer itself. Now, the fourth type, I'm sorry, is active integrated transceivers. And in here, we have a single radiator that is shared between the receiver and transmitter paths. We can have either a diplexer to separate the two frequencies, or we can have an integrated port isolation, like utilizing metamaterial structures, DGS, defective ground structures, or switches. Again, the majority of the works that appeared in literature were not truly AIA. They utilized rat race couplers. They utilized some kind of different paths to do this kind of isolation between the 50 ohm active part and the 50 ohm antenna. And they're just switches to turn off and on the receive and the transmit parts. Again, 50 ohm was maintained in here, so it was not truly active integrated. The same thing was done here. This is a diplexer-less transceiver. There's no diplexer, but we are utilizing defective ground structures to isolate the transmit and receive paths. And again, no active loading was considered. So there are a lot of limitations in the previous works that could have been done, or that where the motivation of coming up with a more integrated approach and a more concise methodology to do this close integration between the active part and the antenna part. Of course, the last type of active interior antennas are other types of active loading, such as frequency agile active interior antennas, or frequency agile antennas and polarization agile antennas. And in these, we use semiconductor switches or transistors to turn on and off some switches, or to load the antenna structure so that we can have some kind of a change in the frequency response to cover multiple frequencies based on, for example, digital switching. For polarization agile active interior antennas, we can actually change the polarization. The orientation of the current over the patch can be switched, and then we can do different kinds of polarization, like linear, left-handed, and right-handed, by making the current circulate from one end to another, comparing to the two input ports. Of course, all of these techniques, some of you have already seen, but the major drawback behind these is the fact that they are all, the majority of them are based on 50 ohm based connection. Where are we at right now? I picked up this paper that is not yet fully published, actually, from a group that is well known, Professor Gabriel Ribiez, University of California, San Diego. And this shows you the state of the art, millimeter wave based antenna arrays for 5G. This is a phased array, 64 elements, dual beam, 28 gigahertz phased array for 5G. You have extremely nice metrics. We have very nice beam forming capability. We have extremely nice integrated chips, 2x4 RF front ends for each. So we have 2x4. 2x4 means 2 polarizations, 4 antennas. Okay, so each 4 antennas have one chip that is giving them the amplitudes and phase excitations in 2 polarizations, vertical and horizontal. Extremely nice, very compact and integrated design, except the antenna was optimized for 50 ohm and the chip was optimized for 50 ohm. Can we do more than that? Well, it depends. It depends on the complexity and on the application, but I will show you in the coming slides that we can improve the efficiency if we do co-design rather than separate design. And this brings me to the main part of this presentation, which is the fact that we would like to have this tight integration between the antenna and the active circuit so that we can have miniaturization, bandwidth increase, better efficiencies, and improved burst isolation. I think I need to speed up a little bit, but I will make sure that the idea is clear. We have seen this, so this is the idea. We want to integrate the active part with the antenna when we do the design. Of course, there are several challenges that need to be overcome. This is a pictorial view of the actual co-design process. We need, of course, to model the antenna as well as the active part in some kind of a simulation environment, and we need to tie them up in the right way so that we eliminate the 50 ohm requirement. So we will have the first example will be an amplifier integrated transmitting antenna. So we have this path, this is the RFN, and this is the antenna. Okay, so we want to co-design, and the idea is conjugate matching with the conjugate impedance of the antenna, because we know that conjugate matching will always guarantee maximum power transfer. Now, this is the design cycle that we will follow in all the examples that I will show you in a minute. We start by antenna modeling. We know its antenna parameters. We take the S parameters of the antenna. We integrate them with the amplifier. We select the actual amplifier metrics based on the load, or having the antenna as a load for the amplifier. Then we will check and co-simulate the two together, and we will see how the actual complete system behaves, and then we will go back and optimize if needed. Of course, in our designs, we used ADS for the active part, for the amplifier design, and we used CST for the integration and the antenna design parts. The key point here is that we want to make sure that gamma L on the Smith chart is the complex conjugate of gamma out on the Smith chart. Gamma out is the output gamma of the unmatched amplifier, and gamma L is the reflection coefficient of the output matching network plus antenna, this whole structure together. So we need to satisfy or go and calculate these two parameters, and we can find the gamma of the antenna from our knowledge of the impedance of the antenna and the impedance of the matching network, and we can utilize some of the relationships that we have taught you guys in amplifier design or in two-port networks to come out and have an expression for gamma out. So we start with an antenna design. We optimize gamma out and gamma S for the transistor. We design the input and output matching networks. And then we will co-simulate the system, and then we will do an iteration to see if our parameters are satisfied or our goals are satisfied or not. Of course, to do this, to have the antenna imported into the circuit simulator, which is ADS, for example, we have to convert the antenna into a two-port network. So to do that conversion, we need to follow this kind of two-port modeling, a step-by-step procedure. It's not that difficult, but it's extremely important to note here that you need to always take the connector effect into account. Here, we are plotting the impedance variation versus frequency on the Smith chart for the measured S11 and the measured S11 with the port element, with the connector. Okay, as you can see, having the connector even at 2 to 3 gigahertz, it will kind of rotate. There will be a phase shift. It will rotate your impedance a little bit on the Smith chart. So you should always de-embed the effect of any connector if you want some accurate results. Of course, we can follow this procedure to come up with a two-port model for the single port antenna and then utilize it in our circuitry later on. But you will see that if you de-embed the effect of the connector, you will have a better matching between the response measured and the actual modeling values if you do the de-embedding before you proceed. The first example that I'm going to show using this kind of co-design methodology is a narrowband AIA. And as you can see here, we start. The first step is the antenna design for a specific band. So we check the antenna for its resonances. And we see that the resonance for this antenna is about 3.5 gigahertz. If we look at the imaginary curve here, XN simulated and XN measured, we will see that the resonant frequency is about at 3.5 gigahertz. Then we proceed with the design of the amplifier. An amplifier that covers, the band of interest that we want. Please note that the original antenna was originating at 2.5, but we will make it work now with a lower frequency based transistor. So this transistor was optimized between 2.4 and 2.6 gigahertz, for example. Okay, but we checked the stability. It's unconditionally stable between 2 to 3 gigahertz. We marked the gain circles, the noise circles, and we made the trade-off between the two, as you all know. And then after that, we will do the antenna loading. So we will load the antenna with our amplifier, and after we convert it to a two-port network. And then after we do that, we actually design the output matching network to make the complex conjugate match with the antenna at the frequency of interest. So remember, we started with an antenna that resonates at 3.5 gigahertz, but with the optimization procedure and the input and the output matching network here, we actually shifted its resonance and shifted its behavior because we're looking at the complex conjugate match. So even though the 50 ohm point was around 3.5 gigahertz, the optimum power or maximum power transfer can be shifted if we have a network like the matching network that translates the impedance of the antenna to the complex conjugate impedance of the amplifier itself, because we're looking at gamma out and gamma L including the matching network. So the matching network can do the frequency translation for the antenna response as well. As you can see here, we have very good matching for the complete structure and a good transmission gain over here, about 8.6 dB. And then when we integrate, when we put back the model of the amplifier in CST, taking into account the actual geometry of the antenna, we see that the efficiency of the antenna is extremely good. Of course, the radiation efficiency, of the antenna itself is very bad, but of the overall system, it is good, because we are not looking at the antenna itself, because the antenna is now completely unmatched, because it is supposed to resonate at 3.5, but now we are operating it at 2.6, right? The resonance here is about, 2.4. So we are working at 2.45 gigahertz rather than 3.5. But yet, the radiation efficiency and the realized gain are according to the maximum that we can get from the amplifier, which means that the antenna is behaving because it is seeing the complex conjugate match at the other side. Wow, time is flying. Okay, so we fabricated this to verify the design. And as you can see here, we tested it in a simple lab environment. We had a transmitting antenna, an ultra-wideband transmitting antenna, our antenna, and we saw that the peak is happening around, it was shifted a little bit to 2.59, but we saw the peak. This is just S21. This is just the absolute power, okay? But again, the measured gain was around 10 dB, like what we expected. Then we went ahead and we measured the response of the active antenna in a SATIMO chamber, and we got good results, 2.1 dBi for the antenna alone, with about 53% radiation efficiency for the antenna alone. The second example, so we did the narrow band, then we did the wideband to test the feasibility and the applicability of the co-design procedure. And we followed the same steps. We did the extraction, the conversion of the antenna into a two-port network. We built the input and output matching networks based on complex conjugate match rather than 50 ohm. And we actually had the antenna cover the frequency band from 2.4 to 2.6 gigahertz with about an amplifier gain of 9.3 dB. So the total gain was about 9.3 plus 2 point something for the patch, and we ended up with about 12 dBi. Of course, it was fabricated and measured, and the measurements and fabrication results kind of correlated. And this is a summary of the two, the transmitting and receiving AIAs with complex conjugate match and tight integration. We were able to actually miniaturize the first antenna from 3.5 to 2.5 gigahertz without doing anything, just by properly conjugate matching it to the amplifier output. The last example that I'm going to show you is ultra-wideband based AIA. So we can apply the same methodology on narrowband, wideband, or ultra-wideband based antenna systems. And here we added the complexity and we said we want to put it in a MIMO configuration. So we designed two paths rather than one, with two antenna elements in a MIMO configuration. So we started with the antenna design. We had this kind of semicircle based ultra-wideband monopoles, and we tested their kind of response. As you can see here, the measured S11 was not that great. We had where is that? The simulated S11 is this. The simulated S11 is the square. So you can see here the square is covering from 1.5 to 3.5 almost, but then the measurement was not very great. It did not cover the same band. It was much narrower in bandwidth. Okay, so the coupling was I think there's a small mistake here. I think the wider band here is the actual S11, and this blue one is the S21. I will verify it in the coming slides. But the idea here is that we had a response from 2.8 to 5.5 gigahertz, and the isolation was less than 10 dB. So this is the isolation actually. And both matching and isolation needs to be improved. So it was not ideal. So we wanted to improve the isolation and response of the antenna by active integration. So we went ahead with the amplifier design. We wanted a wideband amplifier. Again, what we did here, we did a standalone, meaning that a 50 ohm based design for the amplifier. Sorry, this is the gamma of the antenna standalone, and as you can see, it's not that good. But if we do an integration, we can get a little bit further bandwidth in here. Still, this area is not that great. But again, we started with this kind of not that great response, but we wanted to actually convert the antenna response so that we can include it in the amplifier simulations. And then we had this big circuit model that had the amplifier, the matching networks for the 2 paths, and so on and so forth. And then we started the optimization. We did the same procedure, and we optimized all these matching networks, and we ended up with an actual response that spanned from 1.75 to 5.5 gigahertz. And this is an ultra-wideband by definition, as well as extremely nice gain response, about 16 dB. Sorry, this is the total efficiency. The realized gain was about 19 dB with the amplifiers, of course. Now, when we look at the actual frequency response, the standalone isolation was not that great, as you can see in this region. The S11 and S22, the measured responses of S11 and S22 of the integrated antenna are actually below 10 dB, up to about 5.5 gigahertz, as you can see here. But the active integration improved the isolation, as you can see, this cayenne curve and this blue curve. So this blue curve is the curve actually after the integration. As you can see, the isolation is improved by about at least 7 dB. This is just another measurement curve, I guess. This is the fabricated prototype of the actual MIMO active integrated antenna. And as you can see here, the realized gain is very close. We did the ECC. The ECC improved a little bit in the majority of the places. And we had a maximum measured ECC of 0.33. Of course, these were the radiation patterns for different planes. Now, where does that take us? So what I've shown here is that active integration can improve your bandwidth, can improve your matching and bandwidth, as well as it can improve your isolation when you have multi-antenna systems. Not to mention the gain that you will get from the amplifiers. Now, when we look at 5G integrated antennas, like the one that Qualcomm actually announced earlier this year, last year, and it was in production earlier this year, they proposed this kind of millimeter wave based antenna system that has 8 patches and 2 RFICs at the back. And guess what? These are also not really active integrated, because they are based on 50 ohms. I think it's because of the complexity of doing active integration at higher scale and high levels of integration. But still, we can push this and get more if we do this complex conjugate perspective. These can work at 27 to 20. Of course, the results that they showed was only for one frequency, which is 28 gigahertz. And as you can see here, the beamforming that is happening between 40 and minus 40 degrees. This is the actual IC layout. And as I showed in my model before, the antenna arrays at millimeter waves will be placed at 3 locations, as you can see here, so that we can minimize the blockage. So the hand blockage will only just degrade about 18% of the coverage. So you will still end up with very good coverage That's why they decided to go with 3 arrays on the sides. There are a lot of players in the game. So as researchers, we need to make sure that we have innovative works and innovative ideas over all these giants in industry. Some future challenges, well, our mobile handsets will actually encompass a lot of complex-based systems. We have multi-antennas, we have multi-band transceivers, we have energy harvesters and wireless chargers. All of these needs to be integrated together, and this is what we are actually doing in my group at Polytechnique. Of course, this is just a pictorial view of the future complexity of 5G-based architectures. Some potential challenges, these are my own personal views. Active integration and coming up with miniaturized active antennas and front ends is extremely important. And I know several companies that are doing active antennas nowadays. On-chip, on-package, and in-package antenna array solutions are key. Also, there are several players doing that. None of the previous designs that I showed you today, even the Qualcomm and the 2020 paper, are doing on-package. These are all antenna alone, chip alone, and you attach them together. We have to have beamforming in all our future designs. We need to always consider testing and characterization, come up with new efficient CAD design tools and computational electromagnetics. We should always think about health issues, and the next generation will be beyond 100 gigahertz. So we're working towards ultimate integration between antennas, electronics, and algorithms. Finally, I have to ask the audience to ask their libraries to get copies of my books, because they will cover both the antenna side and the active integrated antenna portion as well. With this, I will conclude. Thank you very much for listening, and I will be more than happy to answer any questions. I'm sorry, I think I took exactly 1 hour.
All right, thank you, Prof. But before we take questions, can I ask an audience to take a group photo first? Because
Can you see now this picture?
Yes. Okay.
So here, let me put a pointer. Here's a laser pointer. So the key is here. We want gamma out. We have an almost opposite Lucas. So the output matching network plus because the antenna now is part of is loading your output matching network, right? So when we look at gamma L, this is gamma L from here, looking inside, and this is gamma out, looking into the amplifier. We want gamma L to be the complex conjugate of gamma out, okay?
Right.
So now, even if the antenna is resonating at a little bit higher than the intended frequency, of course, you cannot, for example, shrink it so much, because you will have the effect of, an extremely small aperture, and then maybe you will have a lower efficiency. But you can push it a little bit backwards if you carefully design the output matching network such that the output matching network loaded by the antenna impedance, because the antenna impedance is complex. So with that, when you look at it as a whole, as gamma L, it will behave as the opposite of the output of the amplifier. If we do that, and we follow, you see, here is the catch. Gamma L equals to gamma out conjugate. So we need to satisfy this relationship in our design. And afterwards, of course, we need to convert your antenna into a two-port network. You will put it in ADS. Of course, you extract these, you make the two-port network, you put it in ADS, and then when you design here, you will design the amplifier and its matching network based on the loading condition of the antenna here, okay? So at the end, you will have a complete system. You will put the amplifier S parameters, you will put the antenna two-port S parameters, and then you will have P1 to P out, and then you will have a complete, system response that will follow whatever your design criteria was. So if we go back again, the key point here is this condition. The complex conjugate match, but where? At the output of the output matching network for this chain. For the low noise amplifier, for example, it will be at the other side here. So you will have the antenna with the input matching network matching the input of the amplifier. So we need to look at the gamma N. In this case, it will be gamma N and gamma S. Okay? So depending on the location, where is your antenna with respect to the amplifier, you need to satisfy this condition. Of course, the actual calculation and the step-by-step is actually shown in the papers and in the book. I did not go over them in details, but I mean, once you identify what is gamma L and what is gamma out, it's very simple to get the matching network.
All right.
Yeah.
Right. Thank you, Prof. Thank you for the explanation.
You're most welcome.
We have two more questions. First from Saif Najim Ismail.
Yes.
I have questions about visible light communications. Is it need modulation?
Visible light?
Yes.
Okay. Well, the idea of modulation is actually to put or to transmit. Well, the idea of modulation has more than one aspect. As far I've never worked with visible light, based transmissions. I'm not an optics guy, but from a modulation fundamental knowledge, the idea behind modulation is that we want to put more information within a waveform. So we modulate. Well, initially, the analog modulation was to actually put a low frequency data on a high frequency carrier. At visible light, for example, we have the light, but we still need modulation so that we can code the signals and we can, put more sort of speak, we put more data symbols per signal. So we have, for example, for visible light, we have what we call wave division multiplexing, or we can where we can actually modulate or use different wavelengths to transmit different data paths or different data information. But even there, I mean, I'm not, again, this is a question a little bit out of my domain, but I still believe that we need some kind of modulation, maybe not the one that we are used to with the radio signals, but something similar to encode the data and, of course, encode and decode, as well as maybe increase the amount of data rate per wave or per signature. I'm not sure if this made things worse or clearer.
I hope it's answering this Mr. Saif Najim questions. There is one more questions by Abdul Amir.
Yes.
Prof, are you still there? Oh, okay, sorry. I think my connection is not okay. All right, one more questions from Mr. Abdul Amir. He asked about how to present the inductor and capacitor value into transmission line. Is there a formula? I think you have the formula, right?
Yes.
It's in the book, isn't it?
Well, I mean, for in general, if we okay, is the question about, you know, doing a matching circuit using transmission lines, or his question is what are the values of the capacitors and inductors and the transmission lines? If that was the question, the answer is yes. The actual values of these circuits is in the paper, in the original paper that we did, as well as in the book. I did not put it here because it is not the objective. I mean, they depend on the actual parameters of your design. So if you want, for example, to replicate this design, I will be more than happy to share the paper with you and give you the values. This is not an issue. But if the question was, can I go from LC into a transmission line? Yes, the answer is yes, and there are equations for that, of course.
All right. So I think we need to ask our library to get your book then.
Or I can share the paper with you. Whoever asks for it, I will be more than happy to share it.
All right. Is there any more questions from member of the floor before we close our session today?
Hello.
From our dean, Dr. Azrani.
I have question actually for Prof.
Yes, please.
The first question I think is very relevant to what Dr. Saidatul asked just now, because we actually have some well, I mean, work going on reconfigurable stuff like reconfigure impedance matching and then patterns and others. But the thing is that when they, well, I mean, they reconfigure the impedance matching, at the same time the pattern also change, you know, because sometimes we don't want that to be changed as well. So I think that probably related to your, I mean, the co-design strategy just now you mentioned.
Well, the idea here is that the actual radiation pattern should not be, you know, altered much, because again, the objective is to have gamma L as the complex conjugate of gamma out, where gamma L is the combination of, for here, I'm sorry, this is gamma N and gamma S. The combination of gamma S is actually the antenna gamma and the input matching network gamma. So you might have an alteration in the radiation pattern if the changes are directly connected to the antenna, where it will affect the current distribution on the antenna.
I see. Yeah.
So if the current distribution on the antenna is touched because of the matching network or any electronics connected to it, yes, Changing the current will change the pattern.
Mm.
So in order to avoid that, maybe you need to put a layer, an isolation layer, okay, between the actual control and the antenna, so that it does not, or when you change the control, it does not directly play with, unless, well, here's the catch. It depends on what you are doing. If you are doing direct reconfigurability to the antenna, yes, you will connect your diode or your capacitor or whatever, the circuit, to the antenna so that you change the current, because this is the objective.
True.
Okay, but in our design here, the objective is not to change the pattern, is not to do reconfigurability. The objective is to have better efficiency, better radiation efficiency, and maybe some kind of miniaturization. Okay, so we can do the miniaturization, we can do the efficiency, because here we can guarantee very good efficiency, because the complex conjugate matching is almost always satisfied. And when we do that, then, you know, maximum power transfer will occur and we will have minimum reflection. When I have 50 ohm with 50 ohm, any kind of slight change when you load, I mean, it's 50 ohm with respect to 50 ohm. This is 50 ohm with respect to 50 ohm. But when you load the antenna with the amplifier, you don't know what's happening. This is what we are avoiding. In the sense that our this kind of this foundation is happening because
that all your design able to improve the solution. So it's very well. Matching, probably the isolation is not improving that much, but
Correct.
if you want to decouple it, that probably the matching is not working well. So any tips or any nice recipe for that?
There is no magic recipe, because the thing is that it all depends on the objectives and the application. But for this kind of design, for example, for this 2-element MIMO, okay, it looks tedious, yes, but once you do the procedure, the design procedure, a couple of times, this was actually based on a master thesis. A master student did this, and he, of course, he just got his PhD last week from Canada. But when he did this work with me, he actually published 4 journal papers as a master student, 2 of them in the IEEE. Okay. And the catch is that if you have a dedicated student or a dedicated researcher, he can master the technique and he can do this design in a few months. It seems like a tedious work, but once you master the steps in here, then, you know, taking on a complex system like this one will not take a lot of time from you. It will take a lot of time from you to learn the process. Yes, this is typical. But the advantages that you can get are interesting. You know, we did not expect that we can do multiple objective optimizations with this kind of procedure, and we showed that it can be done. Of course, we did not take it further because we just proved the concept. But there are a lot of things that can be still explored in this domain.
Okay, that's all from me. Back to you, Dr. Sadatul.
Right, thank you, Associate Professor Azrami and Prof. Sharawi for the Q&A. Any more questions from the audience? Before that, oh yeah, we have one more questions. Dear Prof, could you share any reference about matching circuit, please?
Oh, about
By
matching circuits.
Ahmed, yep.
You know, there are very well-known books. You can check Poser's book, Professor David Poser. We have one chapter in our book, in my book as well, the active integrated antennas, about matching. I think maybe you don't need a book. You can have maybe a couple of pages online that can show you exactly the steps. But all RF microwave-based books have a chapter dedicated to impedance matching because it's extremely fundamental to microwave engineers.
Yes, correct. Any more questions from members of the floor? Before we end our session, I think we're going to end it in 5. I think if there's no more questions, we're going to end this webinar. Okay. I think it seems no more questions, Prof.
So should I now pose my questions and make a quiz?
do you have a quiz?
No, I'm just kidding.
I wasn't nervous. I think we should invite Prof again, perhaps to share with us how to publish a paper in AWPL, since you are the editor, isn't it?
Yes, of course.
Yeah, thank you. Any more questions?
But for that, I will charge you. For that, I will charge you the fees.
In that case, we need to discuss with our dean.
Yes, the dean should make the calculations, of course.
I think he endorsed.
Thank you very much, Prof. Thank you very much.
My pleasure.
Thank you very much, Prof.
My pleasure, guys. Thanks for having me. And I wish all the audience and researchers best of luck. And, you know, as I said, if you guys have, you know, questions that I can, you know, answer quickly, I will be more than happy to do that. You can just send me an email and I'll be more than happy to direct you. If I don't have the time, I will just direct you to a reference or something to dig further. So best of luck to everyone, and thanks for having me today.
Thank you very much, Prof. Thank you.
Thank you very much.
So, thank you for audience as well for joining the webinar today. And just to remind you, don't forget to fill up the evaluation form. You may find the link at the chat room. Thank you very much, everybody.
Thank you very much. Bye-bye.
Bye.